All right, so now we'll talk about the next homework briefly, and we'll take a look at, I guess we can take a look at the template. Now I haven't pushed a 64-bit template yet. We'll take a look at the 32-bit template, but there isn't much difference. I'll push it tonight, hopefully. And then we'll get into file systems. It's already the 8th, I think. November 9th even. So it's about time we start talking about file systems, I think. All right, so the next homework is called implementing signals, as we discussed last time. So there's a few steps to it, as usual. And the basic idea is, first we just want to sort of have any sort of signal handling. So there's some code in the template already that has changed kill to be a signal delivery sort of kill, I think, as opposed to just killing the process. Used to be a kill function, I think. Now it does more. It used to just set the killed variable to 1, and now it does something a little different. So first we're implementing this alarm thing. So alarm doesn't make an alarm happen, it sets an alarm, as in a wake-up alarm. Right? So we say, oh, send me a signal after this many seconds. That's what alarm does. It sends this sig alarm signal, that's the idea. And so now we just need to set that up. First add a system call that can accept this request. And then we want to kind of wait until the appropriate amount of time has passed, and then deliver the signal to the application. But in this case, delivering the signal just means killing the process, I think. We don't have any other signal handling yet for the process. So we'll do the default signal, which is die. And then in the next step, we want to be able to set up so that this signal delivery does different things depending on what the user wants. So initially, we just have the default, which is kill it. Or you can set it differently so that now, if the alarm signal comes in, maybe we ignore it. And then finally, we have actually not quite finally. And then we have the user space signal handling. So now we're supposed to run a function in user space. This is, yeah, without a doubt, this is the hard part in the homework. The first two are pretty simple. What's challenging about the last part here is we're supposed to run. Now it's sort of a callback function, right? So we're used to having the user space asking the kernel to do things. But now it's the kernel asking user space to do things, and things have to continue running. So the user passes in using this signal system call. It passes in a function saying, when this signal comes, run this function. Make me run this function. And it's very important. Now you could, in the current setup with x86, you could accidentally run the signal handler in supervisor mode. I don't think it would work once you get to a system call, but at least before you try printing anything, it would work. Not exactly sure what happens, but anyway, the setup here is we have to get to user mode. So we basically have to iretq or sysretq into the signal handler, and then when the signal handler finishes, then we make a new system call, this sigret that takes us back into the kernel and then into where we came from. So it goes a little bit in and out and in and out. Maybe I should draw this. Let's see. Right, so we have the user stack and the kernel stack. Oops. Of course, initially this one is nothing. So the user makes a system call, let's say. It might be read from the console, a blocking system call. So now we have a system call, and now the kernel, we switch over to the kernel stack, and we go a little bit into it, right? And now we're sitting somewhere in a read, and there's a wait. That's what's suspending the process generally. So now we're waiting for, I'm sorry, a sleep. We're sleeping, waiting for console input. Right? Okay, so now this kernel stack is out, and now suddenly one way or another, this signal gets triggered. And in this case, let's talk about the alarm signal, because it's kind of an easy one. We don't rely on any other interrupts, other than the timer interrupt, really. So now we're probably not on this process's kernel stack anymore. Maybe we're on the scheduler stack, perhaps. All right, so an alarm came in, or sorry, a timer interrupt came in, and we're doing the alarm handling. That means we now have to wake up this process, which was running the wait. It stops waiting. That's what happens anytime you get the sleep. Sorry, anytime you get a signal, you have to stop sleeping. That's just how it is. If you want to deliver something, we have to return back to user space to do the delivery, and so what we do is interrupt any ongoing sleep and return an error code or something instead. All right, so this here was the probably timer interrupt. This did a wake up that then wakes up this process after setting some flag saying, okay, this signal needs to be delivered. All right, so in here we were actually, maybe we should make it a little more explicit. Okay, so maybe we have a trap frame, and we have syscall, let's say, read. And that then did a sleep. All right. So that's how it, where it was waiting at the moment. And then we, with this wake up from the timer interrupt, we say, okay, this process is now runnable again. So we come back in here. This got woken up for whatever reason. Needs to come back out. The read turns out, oh, that was a failure. There wasn't anything to read. We back out because there is a signal to be delivered. This is something that you may have to pay attention to. Usually we have a condition wait that says, okay, sleep until there's something to read, right, over and over. But it really should be sleep until there's something to read, or we were killed, right? If we were killed, we should exit, or there's a signal for us. Because if there was a signal for us, we have to return back out here so we can deliver the signal. Okay, so we're going back further out, and somewhere in here, we're in trap ASM probably. Right? We need to see, oh, there's in fact, there's some code already in there that says, let's see if there's a signal to deliver. If there's a signal to deliver, well, then we need to do a little bit of special handling. So in that case, we add a little bit more. Here's a signal frame. We add something to the user stack. We call the function, let's see, signal handler. So we have to modify the RIP or the RCX actually, so that we jump into the signal handler function instead of the getting back to where we used to be. So now we're running the signal handler function for a little bit, and at the top of this thing, we've left a sig.ret function, a pointer. So now at the end, when we're done running a signal handler, we get a ret, and we say, oh, that's a call to the sig.ret function, which in turn makes another. So now we're done with the signal frame because we're at the end. We run the sig.ret thing, which then takes us back into the kernel. Oh, nice. Probably something like this. Actually, I'm not quite sure. Anyway, so now we get another signal system call saying, "Oh, I'm done with my signal handler." And so what we do is, in the end, we just need to return the trap frame to what it used to be before we started handling this whole signal, and then we return again, and then finally we're back. So now we do it pretty much immediately. We just see, oh, that's a sig.ret. Well, let me put this back the way it used to be, and we return to the user space. And now we're running our normal user code wherever we came from. But it's not quite normal, right? Because we interrupted that read. It used to be a blocking read, but then the signal came in and it stopped blocking, and so the read would have returned something bad. It doesn't say like, or it doesn't continue blocking after the signal handling. It just says, oh, I read 0 bytes, or maybe it says some error, like an error code back with something. Oh, I got interrupted, right? That sort of thing is what every system call that blocks has to do on Unix, basically. The reason for this is that otherwise you might end up with an arbitrarily deep kernel stack. So you could imagine if we had a stack that's a little bit deep, it's not just a trap frame anymore. We're waiting in here for something. And then we leave this alone and we just deliver the signal with the stack looking like this. And now the signal handler does something else that blocks. Right? So now it grows because the signal handler went in and was doing another system call all the way in here, and now it's blocking. And now another signal gets delivered and just keeps growing and growing and growing. So now we have unbounded growth of the kernel stack just because of these signal deliveries. So what we're doing, just to be safe, I think what every Unix does, is basically return even from blocking functions to deliver signal. And that's a strange interaction between synchronization and condition weights in particular, perhaps, and signals. All right. So this whole thing with the trap frame looks a little complicated, right? How do we return it so it is in its original state? But really, it's not much. What I did is I just have another trap frame variable in my struct proc, a whole trap frame, and I just copy it. So before I deliver a signal, I just make a copy of the whole thing, a backup copy. It's one line, and then I screw up the trap frame as much as I want to deliver the signal. And once I come back and I see it's a sig.ret, copy from the backup into my normal trap frame, and I'm good to go, and just return. So that was like 2-3 lines of code. All right, so that's the user space handling. And we'll take a little look at the template in a moment. And then finally, there's something special about this Control-C thing, which sometimes isn't entirely obvious, especially if you're in a multi-window sort of setup. If I hit Control-C, right, so here's two windows. Now I hit Control-C. How does SH know that it was the one that should get the control C. Why didn't this one get the control C? Right? There's only the one keyboard. So somehow the kernel decides to deliver it, the control C there and not to that one, and vice versa. How does the kernel know that? The current process, but what is that? In our scheduler, at least in x86, there's no current process. Well, there's like the running process, but that changes all the time.
I'm sorry, I meant correct process, the one which.
But which one is the correct process?
Over here, it's in the context of the other, in that window, that's the process running, right? The other in which you hit Control C.
Both of these processes are running. They're both waiting for keyboard input. Right? There's only one keyboard.
The cell gets the command that gets
What's that?
that means in our x86 there is get CMD, so if we get the control C, so it will know that that cell got command.
Yeah, let's see. So I think I've never tried having two programs read from standard in x86. I don't think there is handling for that. But you would have the same problem there. So if you have, I don't think SH allows this. If you set one in the background, probably there isn't any standard in if you have a background process.
I guess in the last lecture, the process error, I was saying he was trying to read from a.
Yeah, then we got something weird. That's right. But that was in OS X, wasn't it? Yeah. Yeah. So anyway, I guess what's going on here is who gets this keyboard event delivered has nothing to do with the process's normal state. Like it's runnable or running or it's sleeping. It has absolutely no bearing on that stuff. Then there needs to be a separate sort of handling of which process is supposed to get input now. Which process is the foreground process. And so that's just how it works. You have a system call that says, now I'm the foreground process. Or maybe alternatively, if you're the foreground process, maybe you can give it away. Right? Now that we have here there's a window manager, right? So when I click with my mouse pointer, the window manager assigns saying, this bash probably is the one that's supposed to get it, and then bash maybe on its own has delegated it to SH. I'm not sure how, let's see here. It says SSH Linux. So there's some special thing going on in OS X where the window knows what's running inside of bash, right? There's a little bit of special case handling there. I think this bash is a little bit extra clever. Right? It knows that it's running in OS X. Yeah.
What if you scroll with in Chrome without making it format?
Like that?
Yeah. That's something to do with the window manager, right?
Yeah, so I think the window manager has decided where input should go, right? So it's, yeah, in this case, I don't know where this, probably the window manager is getting the mouse events, but keyboard events may be different.
I mean, I know for a fact that in some, I'm not sure what OS X is window manager, but in some Linux window managers, you can have focus on mouse over. So
Right.
wherever you point the mouse, that window will get the focus. So, I mean, so essentially
Yeah.
the OS has control of where the mouse is. So it might.
Yeah, I'm not exactly sure what the relationship is with window managers. So it may well be that the events are delivered to the window manager, and it in turn then delivers to the processes running within it. But anyway, we're sort of we're implementing a very simple version of this here. So we're updating sh to just specify using the system call fgproc, new system call. Just telling the kernel, like, okay, whenever you get keyboard input, it belongs to this process. Like, or in that case, in fact, not even keyboard input, whenever there's a keyboard delivered signal, then who should you deliver it to? That's what this fgproc says. So now sh just needs to tell the kernel which one is the foreground process, right? Because the kernel doesn't know about foreground processes before this. If you say ampersand in bash, I mean, what does that mean? It's just, we're just forking another process. The two look the same to the kernel. So we're specifying which one should be the target of signal delivery. And there could be more than one, I think. Yeah, so anyway, yeah, there's some good hints here on how you should set up the stack for the signal handler function. Right, so let's try to take, I think my solution, I ported it in the last 15 minutes to 64-bit. I don't think I got all of it, but it's a good start. Let's first see how it runs. So the first one is called alarm test, I think. Right. So it set an alarm, and then eventually the alarm went off. Okay, and then alarm test 2. Now it's changing the signal disposition. So there it ignored the signal, I think. Handler was 0, and then we had another, we set the new signal for it. Let's see. Signal 14, that's the alarm. And I don't know which one is. Okay, so 1 means ignore, 0 means kill. 0 is the default, right? So here we set it first. In signal, that's the configuration system call, right? It doesn't mean send the signal, it means here is how we handle signals. So now we say, the program said, ignore any alarms. And then the alarm goes off, and actually it didn't do anything. And then we set it to 0. Same thing went through, except now it was I was supposed to kill it, so now it killed the process at the end. Let's take a look at the alarm test 2. Right. So here we say ignore the alarm, and then we have an alarm after 2 seconds. And we say stop ignoring the alarm after 5 seconds, and then it all dies. All right, and then I think this user space handling didn't actually work out. Let's try it. So handler 27. This is actually a function pointer, and that's the address of my handler function. But I think it actually didn't. Yeah, it didn't do anything. But if I hit Control C, at least it died. So that Control C handling seems to be okay, but yeah, my user space delivery isn't yet working. Probably 4 bytes versus 8 bytes of function pointer somewhere, something like that. Okay. Right. So I'll post the template for this in a bit. We were supposed to look briefly at the template. So here's there's a few things going on. I think the main thing for signal delivery is when we return from any system call, we need to see, oh, is there a signal for us to deliver? And I actually included that part in the assembly, so you don't have to worry about it. Now, as you can tell, this is 32-bit assembly, right? It's ESP and not RSP. But we'll do 64-bit soon enough. So we call this check signals, and that function doesn't do anything right now. Oh. There it is. Oh, actually it does something. So if there's any signal pending, it kills itself. Well, that's fair enough. That's sort of the default handling how it should be. And here, kill. This is the original kill, except now it takes a signal as argument. So that doesn't actually do anything with the signal right now, I think. It just sets it to kill. So we're not quite there for signal delivery, but at least all the calls to kill make sense already throughout the code. Right, so your job then will be to handle this, set it up right so that we have a signal pending, presumably, and then on the alarm side of things, let's see. I don't think there was anything there. Oh yeah, let's take a look at proc.h. Right. Okay. So signal, here are the signals that we need to support. Right. So it's already provided for you. That's very nice. I think if we wanted to be a little more ambitious, we ought to be able to remove the killed flag. Right? And we have a signal pending sig kill instead. I think that would be nice. Right? Something you could try, or something I should do for next semester. There's no difference, I think, between killed and having a signal sig kill pending. That'd be nice. Right. But there's more places like that, right? If in any wait state, like in a blocking read, see all of this stuff? There's a lot of places where we check for if the process is killed. And the reason for this is usually that we're in some sort of loop, and we need actually to exit the loop if the process was killed. We can't just stay there, because then the process never dies. And that's because there's no way to kill a process. Right? A process kills itself. The only way to get rid of it is that it switches to the scheduler after setting itself to not runnable, to zombie. At least that's the only safe way to get rid of it. All right. So yeah, I think that's it. So let's take a quick look at file systems then. There's two ways to think about the term file system. Let's see. And it gets a little confusing, so let's get that out of the way right away. There's a file system design or implementation, and then there's a file system instance. And we use the same term for both. So when you format a disk, right, then that disk suddenly holds a file system, right? A whole bunch of files and directories and headers and all this stuff. And yes, that's a file system, right? But it also has that file system is of a certain kind, right? And that's the design. So we can have multiple file system instances of the same design, even in one machine. You could have lots of file system instances on all these different disks or partitions of a disk and that sort of thing. So generally, I am going to use the two terms sort of interchangeably. If it's not clear which one we're talking about, I'll try to say an instance when it's an instance, right? But yeah, that's a sort of a point of confusion that, and there isn't unfortunately a good other name for these two, as far as I know. All right, so a file system is there to organize permanent storage in a way that makes it easy for a program or a user to find its data, right? And also make it quick and persistent. So even in the face of various kinds of failures, we need to make sure that our files are safe. And maybe more than that, our files are safe, that our file system is safe. It'd be terrible if you have 1 byte going wrong somewhere for whatever reason, and now the whole file system just is unusable. You've lost all of your files in it. Maybe it'd be okay if you lose that 1 byte, or maybe a whole file, but you don't want to lose the whole file system because of one small mistake. And there I mean the file system instance, of course. All right, so let's see. Sort of the goals of a file system design. Overall, what we're provided is a block storage device. We want to offer file and directory structure. It's always the case. Every file system does the same thing. You have this tree of directories and some files in it. Right? We want to have some degree of persistence or fault tolerance. And efficiency. Let's start with those. So there's the unfortunate part. A block storage device. What is that? You have two operations on a block storage device. You have a read like that, and then we have a write. That's it. So, you know, we think about hard drives and flash drives and even network servers, right? An NFS server or something, or occasionally even a tape drive or a floppy disk or a CD, and all these things. All they provide is this: read and write a block number. Yeah. No. This is for a file. This is something that the OS provides, but a seek is basically saying how far into our file did we read so far. You don't really need it. You could just read all the bytes up there, but it's a nice way of jumping forward. And then sometimes we talk about seeking on disks, but that's a different thing. That is the time it takes for the disk to move its read head and the spinning cylinder so that it can read the block number that we specified. And that just takes a very long time. It takes usually 5 to 7 milliseconds. And if you think about that, there's say 1 nanosecond per cycle, like a gigahertz processor. And now if it takes a millisecond to do a block read, that's 1,000,000 times slower. It takes more than that. It takes 5 to 10 milliseconds. So 5 to 10 million times slower to read one of these than to execute an instruction. let's say. So on the order of that. So in principle, we might prefer to execute a million instructions rather than read from the disk. A million instructions is quite a bit. So that gives us a lot of latitude to implement a complicated file system if we can get some more performance out of our disk. Then there's flash drives and such. They have different behaviors. Usually they don't seek. They have much faster, it's still called seek times or access times, but they have other problems. Okay, but in principle this is what we have. So the question then becomes, how do we make a file and directory structure given just this? So, okay, I guess we need to say something more about what a file and directory structure is. So a directory, what is that? It's actually a list of file names. It goes something more like this. File name, and then a file pointer. Let's call it that for now. It's actually called also an inode number. Let's try this out. So if I say ls minus I, here it is. So in this folder here, I have all these file names, and these are inode numbers. If I do it in, there's something a little weird about my Linux folders. Let's try it here. Right, so these are not sizes. I say ls minus I, it shows me the inode numbers. These are pointers, essentially. Pointers to a struct about this file. So these are actually directories, but directories are a kind of file as well. All right, so that's what a directory is. In every file system out there, almost, a directory is this file name and then a pointer. Sometimes they might skip that part and go straight to the contents, but that's unusual. And what's a file? Well, it's a struct. It'll have things like a size. It'll have some permissions. What else? Should go in a file. No, this is on disk. Contents, exactly. So, all right. So because we don't know how big a file is, usually when you make a struct, you say, oh, it's an 80-byte struct, right? But we don't know for a file in general. We don't know how big it is. And it doesn't really fit in one block. So what this ends up being is a list of content blocks. And as we'll find out later, even that is not enough, because a block is 512 bytes by default. And so if you have a 512 megabyte file, which is not unusual, then you have a million of these blocks. And you can't very well fit that in your struct either, at least not at fixed size. Certainly not within 512 bytes. So we'll see how that works out a little bit later. Okay, so when you're as an operating system, you're given a new disk, and the user says, like, show me what's on the disk. All right, what does that mean? Well, it means reading this directory, which is actually a file. A file containing a list of that, right? So it means we're supposed to read some file, the slash file, right? The root directory, and then output this bunch of file names and file pointers. So how do we set this up? Like, if you're a disk, you look like this, right? You're block, 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 block. That's it. And now we're supposed to turn out into something that looks more like a root directory, some other directory, and then inside of there we have a text file, which in turn has, the most important thing it has is a few block pointers. Right? It says the file contents of this thing exist in these 3 blocks. Oh. So if we keep things a little simple for now, let's assume that directory will fit just within 1 block. 512 bytes should be enough for everyone. Directory really needs just some names and some numbers. So it's all right. So we can do it like this. Say this is our let's see. Now this is our 0th block on the disk. It's block 0. Very basic file system. Our block 0 would be this. Right? So if we zoom in here, the contents of block 0 is this list that says home and maybe some other things. And then a number. Number 2. And if there's more entries in this folder, right, then we'll have more lines. All right. So your file system design, file system implementation would have to know that, yeah, you start in block 0. In fact, we might not start in block 0 because there we have our boot sector usually. It usually exists outside of the file system. But the 0th block of the file system, at least, contains the root folder. That's our sort of our initial design here. So you can read that. There's a number of entries. There's probably some limited size of each name. And then there's a number. It says where you can read more about home. Right? Number 2, that's this one, contains home. Actually, let's do that. I say home here. The home folder. Rid of this. But inside of this home folder, it looks something very much like this, right? Right. It just says file.txt, and you can read about it in the, what is that? 1, 0, 1, 2, 3, 4, 5, 6, 7th block. Right. So here's our second folder. We've already made it to 2 folders. So now if you read the first, you see that, oh, there's a folder named home. If you go and read the second block here, you can see the contents of this folder. It says, oh yeah, there exists one file called file.txt. You can read more about it in the 7th block. Inside of the 7th block, which was this one, it goes, this is the file.txt inode. So in here it says size 1024 bytes. And then blocks. What was this? 6, 9, 10. Right. So there's our basic read-only file system. It's already there. So now if you were to read this, you see there's a home folder. You go to block number 2, you read this part, you see there's a file called file.txt. It has more information in block 7. You go to block 7, here it says how big is this file, right? And where are those blocks? In fact, this needs to get a little bigger. Maybe go with that, right? This file is this size, and in fact the contents of the file exist in these blocks in this order. So now if you want to read the first 512 bytes of the file, you go and read block 6, and you're done. Read-only file systems aren't much more complicated than that. The difficult part perhaps would be to kind of pack everything close together so you don't use too many blocks. Where it gets complicated is when you start appending to files or deleting files, moving files around, and perhaps in particular when you're writing to a file system and then suddenly the power goes. Right. So the battery runs out, or if you don't have a battery, there's just no power in the middle of a read, and we don't want to have a destroyed file system after that. It's okay that maybe the file that you were writing to didn't finish writing. I mean, you have to live with that. There was no power in the middle of the write, but we can't lose the whole file system just because that's what we're saying. And that's something we'll spend a lecture or two on later on. Okay, but this is the sort of the basic idea of a file system. Just turn this list of blocks one way or another into this tree structure. Other challenges is this block here, this list of blocks here is usually much longer than whatever fits in a block. So now it has to be a block of blocks of blocks, right? And so on. Okay, we're out of time. Next time we'll do a proper run through of a file system, probably the XV6 file system. That's a very common design, and later on we'll talk about various other ways one can design file systems as well. And I think one of our last homeworks will be a file system as well. All right, I'll see you next week then, and I'll post the homework template as soon as I can.